Okay, let's do another example. Alvin paddled for 2 hours with a 6 km/h current to reach a campsite. The return trip against the same current took 8 hours. Find the speed of Alvin's boat in still water. Okay, I'm going to tell you a secret. You're never going to do this. You're never going to use this in your real life. I don't care who you are. You could be an engineer. You're not going to be solving this particular problem in your real life. So the question becomes, well, why do you teach it? Because it's like an overly simplified version of something that is important later on. And so if you do this one, you'll understand better the problems that come later. Also, it reviews a very handy formula. Do you remember what distance equals? So say you're traveling in a car. Yeah, if you're traveling in a car at a certain constant speed, then you can get the distance by looking at the rate at which you're traveling, the speed, and the time. So it's really an average speed, right? And somebody said it. What does distance equal? Rate times time. So another reason why I go over this problem is because it reviews that formula. It keeps that in your head. So there's some really important ideas within this problem. But later on, the problems become much more realistic, and you kind of don't do these problems anymore. So that's why, you know, I still do these problems because the ideas are really important, but don't think you're going to use this necessarily when you go camping or something. It's not going to happen, right? Okay, so now this is the only one, in this problem, it's the only one where I have a gimmick for solving it, but it's a good gimmick, okay? We're going to create a tic-tac-toe chart, because everybody knows how to create a tic-tac-toe chart, right? Okay, so create a tic-tac-toe chart like so. And at the top of the chart, okay, it has columns, right? The columns run, there's one column, there's another column, there's the other column. So above each column, you're going to put a letter from the formula. Remember the formula, distance equals rate times time. Above the first column, you're going to put distance. Above the line, you can put equals. Above the second column, you're going to put R for rate. On the next line, you can put the dot for times. And then the third column, T for time. And we're going to use this tic-tac-toe chart as a chart to label what we know and what we don't know, okay? Usually there's two objects traveling or two different time periods in which a single object travels. So the first row, okay, what do I mean by a row? Well, a row runs horizontally, right? So there's the first row, there, you know, inside here, that's the second row. Okay, so the first row outside the table, so the distance equals rate times time is above the table. Don't put it inside the squares where you would put X's and O's if you were playing tic-tac-toe. Put it above. And then you're going to label the rows outside to the left of the table. You're going to label the rows, okay, it's only one boat, right? So it's the trip to the campsite and the return trip. So there and back. You can label it however you want, as long as it's understandable. So you could say, you could label the first row there if you want, or to campsite if you want to be more specific. And then, yeah, that's fine. And then back. You could label the second row back, or if you want to be more specific, you could say the return trip. I don't really care how you label it, as long as it's clear what it is that's traveling, right? Or what it is you're analyzing. Okay, so within the first two rows then, I want to fill in distance, in both situations, rate and time. Some of those will be numbers, some of them will be unknowns. So what's the distance? Do we know the distance? But it is the same either way, isn't it? Going to the campsite and going back, same distance, right? So the idea is we could label both. I'll label both with a lowercase d. The distance to the campsite is d. The distance coming back is still d. I don't know what it is, but it's d either way. Would you agree with that statement? Okay. Now, what is it that we're actually looking for? Last sentence. So the speed of the boat in still water. I'm going to let R equal the speed of the boat in still water. Now, in the trip to the campsite, he's going with the current, which means the current is going to add its speed to however fast it's going in still water. Does that make sense? So if the speed in still water is r and the current is 6 kilometers per hour, what's the actual rate going to be on the way to the campsite with the current? The current right at your back, it's going to push you another 6 miles per hour or 6 kilometers per hour, right? So just add in 6. So r plus 6 would be the total rate of Alvin's boat to the campsite. Does that make sense? How long did it take? 2 hours. So t going to the campsite's 2 hours. Now you turn around and you're going against the current. The current stays the same speed under this idealized problem, right? So it's going to take longer when you're paddling against the current because it's going to take away that 6 kilometers per hour from your speed, isn't it? So instead of r plus 6, what's the overall speed or rate going to be when you're going against the current? The speed in still water minus 6 kilometers per hour. Does that make sense? And it's going to take a lot longer. How long does it take? 8 hours. Okay. So notice what I've done within my tic-tac-toe chart. I've actually created 2 equations, 2 unknowns. Do you see them? We've got distance. In the top row, we have distance equals rate times time. Oh, distance, d, equals quantity r plus 6, that's the rate, times time is 2. That's what the first row tells us. What does the second row tell us? The same d equals good. So d equals r minus 6 times 8. Distance equals overall r, uppercase r times uppercase t. So that's lowercase r minus 6 times 8. So as a quantity, r minus 6 times 8. There's 2 equations, 2 unknowns, right? So if we go back to, if we bring it back to Polya's 4 steps of problem solving, we've read the problem, and to help us understand it and organize our information, we created that chart. That's step 1, isn't it? Step 2 is from the chart, we got these 2 equations. So the chart is part of step 1 in Polya's 4 steps. Our plan, step 2, develop a plan where our plan is to solve these 2 equations that we set up. Step 3, we carry out the plan. We're going to solve the system. Step 4, we're going to look back and see if our answer makes common sense. So let's go back and solve this system of equations. Now, what method do you think would work really well here for solving this system? D, in both of those equations, D has to be the same, right? So can't we use some sort of substitution here? So check it out. Couldn't you take this guy and substitute it in for D right there, or vice versa, take this guy, substitute it in for D right here? You'll get the same equation. So if you do that, you get r minus 6 times 8 is equal to r plus 6 times 2. Does everybody see that? The long way to do this problem would be to distribute the 8 and distribute the 2. Distribute the 8 on the left side, 2 on the right side. But there's an easier way, especially because 2 goes into 8 evenly. What could you do to both sides? To solve this a little bit more quickly, you could divide out the 2 on this side. Right? The 2 divided by 2 makes 1, and on the right-hand side then you just have r plus 6. On the left-hand side you end up with r minus 6 times what? 4. And then we don't have a choice. We've got to distribute that 4, don't we? Any questions so far? Okay, distribute the 4. Tell me what you get. So it looks like this. You distribute it here and here. What do you get? 4r minus 24 equals r plus 6. And then what could you do? Get those, make a love connection between those r's, right? Subtract the r's from both sides. Subtract r from both sides. What do you get then? 3r minus 24 equals 6. Everybody see that? And then, okay, add 24 to both sides. What does that give you? 3r equals 30. Divide both sides by 3. 10. It says find the speed of Alvin's boat in still water. Isn't that what we're looking for, r? In fact, it doesn't even ask us to find the speed of the current, does it? Or in this case, it doesn't ask us to find d, does it? We actually know the speed of the current. I misspoke there. Some problems you don't know the speed of the current. Some you don't know d. So it doesn't ask us to find the distance. We could find it, but we don't have to. We're not asked to find it. So r equals what? 10, what are the units? Kilometers per hour. The speed of the boat in still water, that's what we're looking for. The speed of the boat in still water is 10 kilometers per hour, 10 kmh, or I think some books use km division bar h. What's the only step I didn't do in Polya's 4 steps? We didn't check it to see if our answer made sense. You can do that. You can plug directly that 10 kilometers per hour back into both of those equations. Make sure you get the same distance both times. But really what I mean is, does it make common sense? Does 10 kilometers per hour seem reasonable? Yeah, what wouldn't seem reasonable? Like negative 10 kilometers per hour, yeah.